Started. Now let's see. This is what we did in the last class. We started with the operational amplifier. We started with the operational amplifier. And then I mentioned there are two properties that we have to pay attention to when it comes to the MOSFET amplifier, the operational amplifier. Okay, just give me a second. Okay, I'll have to, just give me a second to reconnect it. Okay, so what we did was this. We looked at two properties of operational amplifier. One is the virtual short, and the other is the idea that the current going into an operational amplifier is zero. Okay, let's begin there. Okay, so let's see. Before we go into the operational amplifier, okay, and I said I'm going to start it backwards. Right? I said I was going to start over here. So let me add a page right there. Okay, add a page right there and do a summary of an op-amp. Summary of an op-amp right here. Okay, so it's a 3-terminal device. Sometimes it's 4 terminals, but for our purposes, we simply think of it as a 3-terminal device. Okay, let's see. There's an inverting terminal, negative terminal. There's a non-inverting terminal, positive terminal, and then there's the output. Okay, but sometimes I show, sometimes I don't. There is, and there has to be a power supply. And there's also a negative power supply. Okay, so here is the V input positive, V input negative, and V input positive. And here is the V output. Okay, the big properties that I discussed so far for an op-amp. Okay, this is what I discussed for an op-amp. Let's see. Let's see if I can stroke, make it a bit thick. There you go. Okay, for the op-amp, it's a 3-terminal device. I also mentioned that the gain from the input to the output is really, really large. Extremely large, typically in the order of 10 to the 4 or higher. Okay, that's the open loop gain. Okay, this is the gain when the input is not tied back, or the output is not tied back to the input. Okay, and the input-output relationship is something like this. The output is the difference between the inputs. Let's see, V input plus minus V input minus. So this is one of the inputs that we apply right here. This guy is the input that we apply here, and this guy is the input that we apply here. So the output is a function of the difference between the inputs that is multiplied by gain. The gain is typically shown using A. Okay, that's the gain. The gain multiplies the difference between the input and the output. That's the idea of That's the idea of a differential amplifier, operational amplifier. Okay, so this is an operational amplifier that amplifies the difference between the input and the output terminals. Okay, this is what we discussed so far, and I also mentioned certain properties of operational amplifier that become useful to us. Okay, ideally, the open loop gain is infinity, a very, very large number. Okay, when you think about it, owing to the fact that A is a really large number, and I'm going to show it using the notation that A tends to infinity. Okay, as limit A tends to infinity, as the gain of this approaches a really, really large number. And if the V output is finite, okay, and not the power supply or negative power supply, it is not saturated, then the only implication is that V in plus and V in minus, this difference is really, really, really small. So this tends to 0. Okay, this tends to 0. Okay, let's say I put some numbers on it and it makes sense then. Okay, let's say this is 5. The value of the V output is 5. And this number is really, really large, 10 to the 9. And by the very equation here, then it turns out that this V plus minus V in minus is a really small number, close enough to be a 0. Okay, because if you do V in plus minus V in minus, okay, that's going to be 5 over 10 to the 9, right? This guy is going to come to the other side. Okay, that becomes a very, very small number. So the ideal approximation is, that V in plus equals to V in minus. Okay, so the voltage that I apply on one node will be exactly same as the voltage that I apply on the other, as if they were physically shorted. As if they were physically shorted. That's not the case. They're not physically shorted. They're owing to the fact that this gain is really large number. The inputs, voltages, have to be very small for a finite output. So this is a virtual, and we will see this playing out in a feedback configuration. Okay, so the first principle is called a virtual short. The voltage that I apply on one terminal magically appears on the other terminal. That's one. The second point is easier to see. The second idea is that the amount of current going in, I in, to the positive terminal, and by the same token, I in to the negative terminal, both of these are 0. There is absolutely no current flowing in to the op-amp. Okay, so these are the techniques that we will use. I in plus is I in negative, that is 0. So these are the ideal assumptions that we discussed so far. Okay, and I talk about the idea of virtual short over there. Okay, there's a virtual short, and this also simply means if you're looking into the op-amp, the resistance is infinity. Okay, so if you're looking into any of these terminals of the op-amp, if you were to stand there and look into there is no current flowing in. It's as if the resistance in there is infinity, infinite input resistance and virtual short. These are the assumptions that we make for ideal op-amp scenario. Okay. And let me add one more page to kind of quickly review what we did in terms of the op-amp output saturation. Okay, so let me copy this really quickly. Okay, copy that. Okay, if we were to change the input versus output, if you were to plot the input versus output relationship here, okay, along the x-axis, okay, on the x and y axis, if you were to plot the input versus output relationship, okay, okay, so let me see if I can make some more room here. Okay, there you go. Along the x-axis, I'm going to plot the difference between the inputs, V in plus, minus, V in minus. That's the differential input. Along the y-axis, I'm going to plot the output, V output. Okay, what we saw was that the output is going to be a straight line. Okay, the output is going to be a straight line, right? The output was a straight line, and the slope of that was A, and then it's going to saturate at V positive and V negative terminals. Okay, it was going to saturate at V positive and V negative terminals. Okay, so the idea simply is that this guy, the slope of this guy is the gain. Okay, what's the slope? The slope is change in V out for change in V input, right? I'm going to define V input as the difference between V in positive and V in negative. I know for a fact V output is an amplified version of the V input, right? That's all I'm saying here. The slope of this guy is change in Y over change in X, right? So that slope is the gain. Okay, and then like I said, we cannot, if we are jumping on a trampoline inside a house, we cannot jump above the power supply or above the ceiling. That's going to be the top we can reach, and we cannot go any below the negative power supply, which is the negative VCC. So these set the limits. Okay.
So this is
Questions, please.
These would be where your slope goes to 0. Those are your max saturation in either direction. And like, do we call these critical numbers anything unique?
The critical numbers as in which specifically do you mean?
Say where you have your positive VCC there, and then slope goes to 0. That's your
Yes,
saturation. Positive
yes.
saturation. Okay, so we'll just that V out is the top end and the bottom end.
Correct, and they're limited by power supplies. We can say they're their power supplies that supply the limits there.
Okay, thank you.
Okay, yeah, so they're saturated on either ends, on the top and on the bottom, and in between there's a linear region of operation, and we want to operate in between the saturation regions through the linear region. Okay, that's the region of operation for us. Okay, this is what we discussed so far. Okay, now what I'm going to do is to put circuits around the op-amp. And like I mentioned in the last class, this is called an inverting configuration. First of all, let's pay attention to something. Okay, so far we have only seen an open loop configuration where an op-amp input is applied like so, and the output is gain times the input. But here, something different is happening. I'm doing a feedback from the output back into the input. I'm feeding a part of the output back into the input. So this is called a feedback configuration. And because the output is feeding back into the negative terminal, this is called a negative feedback. Okay, this is called a negative feedback. Oops, I want to do this. Negative feedback. Okay, and we'll see that positive feedback leads to oscillations. The output is going to increase and saturate at the power supplies if we include positive feedback. So for all our circuits in this class, okay, we are going to do only negative feedback. Okay, so let's try to understand the topology of the inverting amplifier here. Okay, first of all, the positive terminal is tied to ground. Okay, the positive terminal is tied to ground, and the input, this guy, the input is applied to the negative terminal. Okay, so if you were to look at the input-output relationship, if the blue wave, deep blue, or the black wave, sine wave shown is the input, the output, you would expect it to be inverted and also amplified. Okay, and let's try to see why that is the case. Okay, we'll quickly see why that is the case. Okay, let's see inverting amplifier. Okay, so the idea that we will follow here is, just give me 1 second. Okay, the idea that we are going to follow here is that okay, the first principle that we are going to apply is, you remember, when we are analyzing this circuit, I'll come back to show you this result. There are two assumptions I made: the virtual short. Okay, the virtual short assumption is that whatever voltage is applied here happens to be the same over there. And it seems for a fact that I'm applying a ground, I'm tying it to the ground. Okay, so as a result, the voltage here is going to be 0 volts. So if you were to call this V at the negative terminal, Vn, that should equal V positive, which should equal 0. Okay, in the last equation I showed Vn to be V in negative and V positive to be V input positive. Okay, but for the change in names, okay, they're still the same. V input negative is equals to the V input positive. Both of them should be connected to ground. Okay, so let's do the analysis now. So now it comes down to a matter of simple analysis. The second idea is that the current that is flowing in through this resistance, okay, that should be the current flowing out through that resistance here. Because if you think about it, the other ideal op-amp assumption is that this current IN is 0. Okay, so by applying these two principles, okay, by applying these two principles, I should be able to get the relationship between V output and V input, which is the source. Okay, so let's see if we can derive that. Okay, so the first thing I'm going to do is to look at that node right there and write the node equation. Okay, if I were to write the node equation for these, for the directions that I have shown here, okay, so the sum of currents at this node should equate 0. So there are three currents, IS, IF, and IN, three currents. I sum them to be 0. So this guy is IS. Okay, that's the current negative IS leaving that node, plus the current leaving this node IN, and then there is the negative IF. Okay, because I have shown IF to be coming into the node, when I'm adding the currents leaving the node, all I have to do is incorporate a negative sign. Okay, or you could even do something that I mentioned in the last class. Just keep the directions like so. Okay, what's the value of IS? Vs minus this potential 0 by Rs. That's the value of Is. Okay, what's the value of Vf? Vf is this potential V0 minus this potential, which is 0 over Rf. Okay, so what's this current? That's 0. So the idea is the currents coming in, the sum of the currents coming in, which is IS plus IF, should equal the current leaving the node, which is 0. So there is more than one ways to do the exact same, arrive at the exact same result. Okay, so I could have as well added Vs minus 0 over Rs plus V naught minus 0 over Rf. These are the currents entering, should equal the current leaving, which is IN. Okay, and then so we see Vs over Rs plus V naught over Rf equals to, this guy is 0, right? That's the ideal op-amp assumption. Okay, that guy is 0. So all I'm doing is I'm adding IS plus IF equals to IN. We have currents entering equals to the currents leaving. That's one way to look at the problem. Or the other way is to look at the currents leaving this node. Okay, there's a negative IS leaving this node, so that's this guy. There's IN leaving this node, and there's a negative IF leaving this node. Sum all of them to 0. So there's more than one ways to solve that problem. Okay, so that's the idea of. Oops, I didn't want to do that. Just this part. Okay, so that's the idea of the node equation, and we have applied two of those principles. Okay, the second principle is that the IN is 0. Okay, that's the second principle. Okay, so now it comes down to, this guy goes to 0 because of virtual short. This guy goes to 0 because of virtual short. This guy is 0 because of the second input current, second assumption. Input current is 0. Now, like I mentioned, Vs over Rs plus V naught over Rs is 0. Okay, and then I can manipulate V output to be expressed in terms of Vs and Rf. Okay, so the result is, once I do that, the result is that V output is V input times this ratio Rf over Rs. Okay, this is called this ratio Rf over Rs. This guy is called the closed loop gain. Okay, let me highlight that right over here. Okay, this guy is negative Rf over Rs is called the closed loop gain of inverting amplifier. Okay, Intuitively, if you try to make sense of this equation, all it says is that the output, okay, the output right here is an amplified version and also an inverted version. That's what the negative sign says of the input. Okay, if the input is like so, okay, the output is going to be an inverted and amplified version. So this guy is V output or VO. So I use these terms interchangeably. This guy is Vn. Okay, Vs is the input voltage. Questions, please.
Will we be doing an example of this?
Yes, you can do an example right here.
Okay, perfect.
Okay. All right. So the question is, find the range of input voltages. Okay. What input voltages keeps the op-amp in the linear region? We discussed the idea of a linear region. Right? There is this input range. Okay, and the output is going to saturate around the power supplies. The output is going to saturate at the ceiling, which is 15 volts, and the negative power supply, which is negative 15 volts. Okay, that's going to be the range of the output. The output is going to range from negative 15 to positive 15. Okay, given this configuration, if you see a configuration like this, and you're going to encounter this over and over and over again, okay, the configuration is that the input terminal, the positive input terminal is tied to ground, okay, and the input, okay, the input signal is applied to the negative side, okay, and then the output is tied back into the negative side as well. Okay, so this is the basic configuration that we are looking for. The input is, the positive terminal is grounded, the signal is applied to the negative terminal, and the feedback is also connected on the negative terminal. So you know for a fact that this is an inverting amplifier. Okay, it's an inverting amplifier, and for all intents and purposes, I'm going to consider this as ground, because there is a short between the two input terminals, right? So if one terminal is ground, the negative terminal is also going to be at ground, okay? So we're going to use the formula that we just derived, V out minus RF over RS is the expression for V output voltage, okay? So this guy, negative 12, is the closed loop gain. That's going to multiply the input to give you the output, okay? And the idea is you want your output, VO, to be in between the positive and negative terminals, okay? If you want the output to be in between positive and negative terminals, it's just a matter of replacing this 12 VO with the corresponding value in terms of Vs, negative 12 Vs, which implies Vs should be in between 1.25 volts and negative 1.25 volts. Okay, as long as the input is in between the positive power supply, positive 1.25 and negative 1.25 volts, then the output is going to be between positive and negative 15 volts. Does that make sense? Okay, if I were to plot it along the x and y axis, okay, along the x and y axis, I want to be sure that this is passing through origin. Okay, when I'm doing that, the x-axis represents the Vs, input voltage, and the y-axis represents the V output. Okay, let's say this guy represents the negative Vs. Okay, that represents the negative Vs. Okay, so what happens is when the x-axis is changing from 1.25 to negative 1.25, the y-axis is changing from 15 to negative 15. Does that make sense? So if we were to go beyond this along the x-axis, the output is going to be a constant 15 volts. It's not going to change. It's going to saturate at the output. Okay, so the idea is when you see this configuration, okay, the positive terminal tied to ground, the negative terminal is where the input signal is applied, and then the output is tied back through a resistance into the negative terminal. Then the two assumptions that we made about ideal op-amp kick into action. The first assumption is that the virtual ground, because of virtual short, what happens is the voltage that I apply on the positive voltage magically appears there as well, and that makes it ground as well. Okay. The other assumption is that the current going into the op-amp is 0. So all the current coming into this branch will have 3D through that branch. Questions, please. Questions so far? We'll come back to look at some problems on this as well. Okay, we definitely will come back to look at some problems on this, example problems. But for now, let's move on to see if we can do a not a summing amplifier, but a non-inverting amplifier. Okay, let's do a non-inverting amplifier. Let me see if I can copy that. Okay, let me see if I can copy this and do this problem by hand rather than showing it on. Okay, here is a non-inverting amplifier analysis. This is a non-inverting amplifier. Let's try to understand this guy. Okay, look where the signal is applied. The signal is applied to the positive terminal. Earlier in the inverting configuration, the signal is applied to the negative terminal, remember? Not so in the non-inverting amplifier. In fact, the very idea of non-inverting amplifier is that I'm applying an input to the non-inverting or positive terminal. Okay, and the rest is still the same. The output is fed back into the input, the negative input. Okay, a bit of a spoiler alert. The output for this guy, V output, is going to be V input, which is VG, times 1 plus RF over RS. Okay, that is what we would expect when we do the analysis for this. Okay, non-inverting amplifier, when we do the analysis, that's going to be the output here. Okay, so let's follow this and see the analysis that we get here in this case. Okay, the idea is that Vn minus V0 is Vn minus V0 is this guy, Vn minus, okay. Now, let's see this voltage. Let's try to find the value for this voltage. First things first, what's the value? What's the voltage at that guy? Let's call this V positive. What's the voltage there? I'll give you a hint, okay? In order to find Vt, all you have to do is you have to start with Vg, okay? And subtract the voltage drop in this resistance, Rg. So there's a resistance Rg, right? Does that make sense? So Vg minus the voltage drop across this resistance. What would be the value of the voltage drop across this resistance? In order to do that, I have to know the value for IP, right? What's the value of IP that's going through the resistance here?
Is it not just going to be that source, that negative source voltage?
It's going to be the negative source voltage, as in this guy.
Oh no, I was thinking of from VG, but maybe I was looking at the wrong node.
The VG, right? Yeah, that's the positive source voltage, correct?
Oh, excuse me, yeah.
Yeah, so that's correct, because the IP, the current going in here is 0. The current going into the op-amp, remember, was 0. So the current flowing through this resistance would be 0. So there's no voltage drop across this resistance. So whatever voltage is applied here shows up over there. That's owing to the fact that this current IP is 0. Everybody with me so far? Okay, so I know for a fact that VP is going to be the VG, that's the supplied voltage, that's the voltage that we are applying. Now I can go ahead, and this is owing to the fact that I know Rn is infinity. Okay, that's the principle that I'm applying here. The input resistance is infinity, meaning that the input current of an op-amp is 0. So very good. Now I'm going to, I'm able to make the second leap, which is the virtual short. Okay, and I'm able to declare the value at that node to be equals to VG as well. Okay, because V positive should equal V negative in an ideal op-amp. Okay, because of the idea of virtual short that we already discussed. Okay, so the next leap that we can make is the feedback forces the value at this guy. Okay, V negative. So this is V positive. This is V negative. Voltage at the positive terminal and voltage at the negative input terminal. And I know that V negative is going to be equals to V positive is going to be the applied input voltage VG. Okay, I'm comfortable expressing the voltages in VG because that's the input voltage that I'm applying. Okay, this is the input voltage that is being applied. Now we are ready to do the KCL. Okay, KCL at node Vn. That's this guy. Okay, that's Vn. At this node right here. This guy. Make sense? Okay, let's do the KCL at that node. All we have to do is to look at the currents. leaving this node. Okay, add the currents leaving this node. There are three currents. There is one current leaving this way. There is one current leaving through this resistance RS, and there is one current going into the op-amp. Okay, there is currents IS, that's the current through the IS resistance. There is going to be IF current, and there's also teeny tiny branch over here, IN. Okay, let's apply KCL at node VN. Okay, that implies IS, that's the current leaving this node, plus IF, that's the current leaving through this branch, okay, plus IN, that's the current into the op-amp. All of that should equal 0. That's the idea of KCL, right? So let's try to do this. VG, okay, this is VG as well, okay, because of virtual shock. So if I start by writing the current flowing in this direction, that's going to be VG minus 0 over that resistance, okay? That's the voltage drop between these two terminals of the resistance, okay? VG minus 0 over RS. That's the value of IS, right? So IS is going to be written as VG minus 0 over RS, okay? And IF, the current IF that's leaving in this direction is this voltage, which is VG. So IF is VG minus the output voltage.
Professor, one thing. How did you get VG minus 0?
Yes. So
How
I'm
did,
interested in finding the current through this resistance, right?
yes.
Right? So through this resistance in this direction, that is what I called IS, right?
Yes.
So the voltage on this node minus the voltage on this node by RS. But the voltage on this node is ground.
Oh, so they go rounded down towards VG, that's why.
Yes. Yes,
Got
that
it.
guy is connected to ground, right?
Yes.
Okay. Make sense? That's a good
Yes,
question.
thank you.
Thank you. Yep. So by the same argument, so that's the expression for IS. Okay, all of that is the expression for IS. Let's try to get, oops, I wanted to do this. Let's try to get the expression for IF. IF, I defined it to be in this direction. So IF is going to be this voltage, which is VG, minus this voltage, which is V output over RF. So IF is going to be VG minus VO over RF. Okay, let me copy that over here. Let me copy that, okay, in place of IF, okay, IF. And what's the value of IN? IN is that current in here. So the node had 3 branches. So the blue node had 3 branches. This guy had 3 branches, and we are adding up the current leaving in each of these branches. So what would be the value for IN? What's the current going into the op-amp?
It should just be 0, correct?
Thank you. That's 0, right? The current going into the negative terminal of an op-amp is the same as the current going into the positive terminal of an op-amp, which is 0. Okay, so now what we can do is massage this equation. Okay, let me just do it in the interest of completeness. So I'm going to write it out here as VG minus 0 over RS plus VG minus V0 over RF, all of that equals 0. Okay, so I can factor out VG in here. I'm going to get 1 over RS plus 1 over RF. That's factoring out VG. I'm left with V0 over RF. All of that equals to 0. So meaning I can take this to the other side and write it as this guy equals to that guy. Okay, so VG RS times RF, RF plus RS equals to V0 over RF. I took the product of, this is simply the equivalent of 1 over RS plus 1 over RF. Okay, so I can cancel, oops, I can cancel RF on either side. I'm going to be left with V output equals to VG times RF, RS plus RF over RS. Okay, simply meaning that V output equals to VG times 1 plus RF over RS. Okay, sure enough. Okay, sure enough, that's the solution that we were expecting. Copy this. Okay, that's the solution we were expecting, right? So the only thing that we want to understand intuitively from this is the input voltage is multiplied by a positive gain. So this guy is positive gain. Here is the input voltage. This is the output voltage. Okay, so if you were to plot this, this is your input. That's your input. The output is going to look an amplified version, but still in phase with the input. Okay, so this is V output. This guy is V input, shown in red, or VG. Okay, does that make sense? So the input is amplified by a gain, which is positive, and then that gives you the output. Questions, please. Questions so far? Okay, so let me summarize. Let me go back to the summary page and add them. Add my conclusions to the summary page. Op-amp summary. Where is that guy? Op-amp summary, page 1. Okay, and I'm going to copy this simply. Copy that. And call this page 2. Okay, and I'm going to add another page here. Okay. So let's quickly summarize what we have done so far. We looked at 2 configurations of op-amps. All right, so the inverting configuration. There is a negative terminal, positive terminal. The positive input is tied to the ground. Okay, the input of the signal Vs is applied to the input terminal, negative input terminal. The V output is measured across here. That's V output. And don't forget the feedback, negative feedback. Okay, this value is the feedback resistance RF. This is the source resistance RS. Okay. Now the expression for this inverting configuration, and we call this inverting Op-Amp. Okay. We call this inverting operational amplifier configuration because the V output is V input times negative RF over RS. Okay. It's a big negative sign over there. This is the inverting amplifier configuration. Okay. Now, there's also a non-inverting amplifier that we looked at. Okay. Let's see, non-inverting amplifier, which is still an op-amp. Okay, which is still an operational amplifier, negative, positive. Okay, there is this RS that still did not change. Okay, the feedback configuration that did not change from the previous configuration. Okay, this time the only thing that changed was I removed the signal source from the input terminal. This signal source, okay, that was sitting in the negative inverting configuration, that's removed. Okay, I got rid of it, and in place of that, I applied a voltage source to the positive terminal. Okay, the signal is applied to the positive terminal, hence the name non-inverting. And I don't remember the name for the resistance that we gave over here, but it doesn't matter. We'll call this VA, and the RA, and the input source was VIN. V output was this guy. Okay, V output is this guy. Now, the non-inverting amplifier. Okay, the idea of the non-inverting amplifier is the output is a multiplication of input by a positive gain. Okay, that's the idea of non-inverting amplifier. Okay, that's the primary result of the non-inverting amplifier. Questions, please. Questions so far. So that's what we did so far. We looked at a non-inverting configuration and an inverting configuration. Okay, and the reason I want to go back and forth and not follow the order given in the slides here is that I want to follow the most logical route. Okay, we started with an inverting configuration, the simplest there can be, that we ground one of the input terminals, the positive terminal, tie a feedback, and then do the analysis at that node, KCL at that node. Similarly, we do a KCL at this node. Okay, we do a KCL at this node to give us the expression for VO in terms of VG. Okay, let's see what else we have to see. Okay, let's see, we started looking at the inverting amplifier configuration. Okay, then we have to go into the, we did a problem here. Then we did not do the summing amplifier. Okay, okay, without looking at what is to come. Is this going to be an inverting or a non-inverting amplifier?
I believe it will be inverting because it's on the negative terminal.
Correct. The inputs, which are VA, VB, and VC, the signals, the input signals, look where they are applied. They're applied to the negative terminal. So the output should really be an inverse or a negative of the input. So sure enough, if you look at this result, the V output is VA times that guy, okay? VB times a negative gain. So let me highlight just the negative component of it, okay? There's a negative gain. VC times is a negative component in there. Okay, so it's an inverting amplifier because VA is just applied to the negative terminal, VB is applied to the negative terminal. And as a matter of fact, if you look at these in isolation, okay, for a moment, let me do this. Okay, for a minute, what I'm going to do is to take away these from the circuit. Okay, so then what do you see? All we see is the good old inverting configuration. Okay, the positive terminal is tied to ground, the negative terminal, an input VA is applied. Okay, and then that is applied through RA, and then there's a feedback resistance RF. Okay, so that guy, this guy, okay, all of this, oops, let me go back and still hide this part. Okay, all of this, okay, this VA corresponds to the negative amplifier, inverting amplifier configuration here. Okay, so if you were to remove all of that, okay, well, what do we have? We have our good old inverting amplifier configuration. Okay, then we can add another branch over here, that guy, and that guy corresponds to the, okay, let me see. Let me carefully color code this. This branch corresponds to the blue terminal in there. Okay. Similarly, as you will see, the green branch here corresponds to the VC inverting amplifier configuration. Okay. So all we are doing is configuring three inputs to be summing. Okay, three inputs to be summing at this node. Okay, so corresponding to that, we will see that it's an inverting amplifier configuration. Okay, we'll do this. We'll do this by hand. But then before we do that, I just wanted to give you an intuition of the summing amplifier configuration. There are three separate inputs added at that node. Okay, and then as a result, we have this sum over here. Okay, so this is what I'm going to do. Let's begin the analysis of this guy by copying. Right? Okay, the summing amplifier. And I'm going to add a page over here and say paste image. Okay, let's do the summing amplifier analysis. Let's do the analysis for summing amplifier. So we are going to retrace the steps that we have learned so far. Step number 1 is to notice that the V positive, okay, or the voltage at the positive terminal is ground. Okay, that implies because of virtual ground, what can you tell me about V negative, or this voltage at that node?
That it's also 0.
It's also 0. That's going to be virtual ground. So that's the very first step we do. We look for the voltage on the feedback node. and see if we can express it in terms of some kind of known voltage. Okay, in this case, it's very well known to be ground, so that solves the problem for us. The step number 2 is to notice that IN, the IN value, which is the current going in to the op-amp over here, that is IN, shown to be IN over here, that guy is essentially 0. Okay, that's the application of the 2 assumptions, ideal op-amp assumptions that we discussed. Okay, so IN is essentially 0. Okay, the current going in is 0. Now, step 3 is KCL at node Vn. So let's call this node, this guy, Vn. Okay, let's look at the KCL at node Vn. Okay, I don't know, how do you want to define the currents, directions here? Okay, there are 4 branches. There is 1. Let me see if I can pick a different color so it shows clearly. There is 1. Okay, there's a second branch. There's a third branch. Okay, all of these coming into this node. There's a 4th branch. There's a 5th branch. There are 5 different branches at that node, right? How do you want to, it's your choice, and we'll follow your choice in terms of the currents. Which directions do you want to pick for the current in the top branch, RA, that current? Do you want it from left to right or right to left? It's your choice. You can pick any direction that you want to pick, and we'll stick with that direction throughout the problem.
Suppose we could just go left to right.
From left to right. The same for RB as well. RC as well.
Yeah, sure.
And RF.
Yeah,
So
just
this
to make
is
the convention
IA.
easy.
Yes, IB, IC, IF, and don't forget this IN that is going into the op-amp, like so. That's IN. Okay. Okay. So what I can do is the same application of KCL. I'm going to make my life easy and say currents coming in equals to the currents flowing out. Okay, once you define the current directions, that becomes easy. Now let's say just for example, if I define the currents to be in this fashion, okay, all the currents are going out, then I would write an equation that says, if I call this IA prime, IB prime, IC prime, and IF, then I would say the currents leaving, the sum of all the currents leaving IF plus IA prime plus IB prime plus IC prime plus IN. That's all the currents leaving, all of them equate to 0. And the idea is both of these are exactly the same. Okay, when you account for the proper directions, polarity, it doesn't matter which way you write. Okay, as long as you are careful noticing the polarities across the 2 terminals. Okay, they are identical. Both of these ways of writing the KCL equation are valid. Okay, so let's see IA. IA is flowing in this direction. So the voltage at the left minus the voltage on the right by this resistance. Okay, so voltage on the left is what? VA. Remember, that's the one of the input voltages that I'm applying. Okay, so IA is going to be this guy. IA is going to be VA minus the voltage on this node, right, which is the same as this node. All of that is the same. VN over RA. Okay, that's the current IA for me. Okay, I can write IB as well. IB is going to be VB minus VN over RB plus VC, which is this voltage, the voltage that I apply here, VC, minus 0, or this voltage VN over RC. Okay, all of that should sum to IF. What's the value of IF? IF is this current flowing in here. Okay, that's going to be the voltage on this node minus the voltage on that node over RS. Okay, so the voltage on the node on the left is VN minus the right voltage is VO. It's this guy, right? The voltage on the right is VO over RS. Okay, so let's see if I can make these simplifications, and don't even worry about IN because IN is 0, right? So plus IN, that's the equation that I get from here. So I'm going to write VA over RA. This guy is 0, VN is 0 because that's the virtual ground, right? Plus VB over RB plus VC over RC. Okay, currents entering equals to the currents leaving. VN is 0 again, negative V0 over RS plus IN is 0. Okay, so that's the idea. Now what we can do is we can massage this equation. If only I can pull up all of these. Okay, just a touch. Okay, now I can say V naught equals to VA times multiply both sides of the equation by RF. Okay, then the RF is going to cancel and show up on the other side, plus VB times negative RF over RB plus VC times negative RF over RC. Does it make sense?
Yes, it does.
Now the idea is I'm applying 3 inputs, VA, VB, and VC. Okay, I'm applying 3 inputs, right? VA, VB, and VC. And what's the resultant output? The resultant output is, just give me a second so I can clean this up a touch. Okay, the resultant output IF is going to be that guy. Okay, when I add 3 inputs, when I'm applying 3 inputs to the inverting terminal, okay, let me do this, VA, VB, and VC. The output, this guy, okay, the output is a sum essentially of VA multiplied by some gain, VB multiplied by gain, VC multiplied by gain. Okay. So let me write this equation one more time just so it's absolutely dead clear. Okay, V output is going to be VA times some gain plus VB times some gain, okay, plus VC times some gain, okay? And that's the reason why we like to call it a summing amplifier, because all the inputs A, B, C are really summed, okay? But don't forget the negative sign over here. It's still inverting summing amplifier, okay? This guy is still a summing amplifier, but inverting, okay? Each of these inputs is weighted by a gain, A1, this is a gain A2, this is a gain A3. So they're weighted differently. So if you want to add 3 different inputs in 3 different proportions, well, all you could do is you could pick one value for RF and pick different, you have a choice of RA, RB, and RC, play around with those values to get the proportions that you want. Does that make sense? So here is an inverting summing amplifier. I don't know if they call it an inverting summing amplifier, but let's see, what do they call it? They call it the summing amplifier. But do you know from the equation that it is an inverting summing amplifier? Does that make sense?
Yes, it does.
Okay. But if you want to make it a positive, what you will do is you put another inverting amplifier in here, okay, with a gain of 1. Then what you will get is a positive sum, okay? All you have to do is to add another op-amp if you want to convert this negative back to positive, okay? A net positive summation can quickly be achieved by passing the first circuit's output to another inverting amplifier with a gain of 1, okay? So that's something you want to pay attention to. Questions, please. Questions so far? Okay, and then there can be the difference amplifier circuit. See the difference. Instead of applying the input as just at one terminal, you apply input at both the terminals. That's all there is to it. Okay, we'll come back. I don't want to overextend here. We'll stop here. We'll come back, look at this difference amplifier, and also look at some problems in the coming class. Okay, let's see. Let me quickly do, if I can add a summary page here. Okay, this is the idea we have been following for op-amps, right? For this chapter in op-amps, I have been writing a summary page. Okay, let me add a summary page here. Copy that. Okay, I'm going to paste it over here and call it a page 4. Okay, the idea is that I have an amplifier that is, let's see. Okay, let's apply negative terminal, positive terminal. The positive terminal is tied to ground. There are 3 inputs that are applied to the plus minus VA. And there is another branch, RB, connecting to plus minus VB. Okay, there's yet another branch, RC, and I can keep going on with any number of branches that I want, VC. Okay, in this case, there is still a negative inverting configuration and negative feedback RF. Okay, this guy is V out. Okay, that's VO. Okay, so V output is VA times negative RF over RA plus VB times negative RF over RB plus VC times negative RF over RC. Okay, excuse me if this is boring you a bit, but I like to repeat myself a bunch of different times and beat certain concepts to death. Okay, so that's the idea of a summing amplifier. This is a summing amplifier. It's inverting. So we looked at three circuits so far: a summing amplifier, a non-inverting amplifier, and then an inverting amplifier. Okay, there is an inverting amplifier, there is a non-inverting amplifier, and then there is a summing amplifier. Three circuits. We'll stop here. We'll come back and do some more problems on op-amps, and let's see how we are doing with this syllabus really quickly. Okay, today is the 16th. So we should really be we should really have been working on the test voltage, test current method, which we happily completed a long time ago, and we are ahead. Okay, we are actually 2 classes ahead in op-amps, which is a good thing. It gives us enough time to work on some problems. So tomorrow and the day after, I'll talk about op-amp problems, and then maybe finish up on op-amps and give you a heads up, give you a leg up on inductors, capacitance, and series. That way, it's not getting too tight to the exam too. If we deal with inductor and capacitance before the weekend, if that is possible, that will give you a little more time for chapter 6 to work on